Here we'll make a quick look at visible molecular fluorescence spectrometry. This part is in Harris' textbook at several different places. Molecular. So first, what's luminescence? Photon is absorbed and then re-emitted from the same molecule at different wavelengths, like this. Absorption, re-emission. Re-emission is going in any direction. Fluorescence is photoluminescence process at which atoms or molecules are excited by absorption of electromagnetic radiation. Excited species relax to the ground state, giving up their excess energy as photons. Fluorescence occurs at 10 to the negative 5 second scale or less. It can be at 10 to the negative 9. In contrast, phosphorescence may last microseconds, seconds, several minutes, or even hours. Fluorescence is much widely used for chemical analysis than phosphorescence. Molecular fluorescence bands are mostly made of lines that are longer wavelengths and just lower in energy than band of absorbed radiation responsible for their excitation. This shift to longer wavelengths is called Stokes shift. Because difference between vibrational states is about the same for both ground and excited states, absorption or excitation spectrum and fluorescence spectrum of compound often appear as approximately mirror images of one another with overlap near origin transitions. So this is excitation spectrum. Now to excite, photons need to be absorbed, so it's essentially absorption spectrum. And this is emission spectrum. These peak practically coincide. These and these are mirror. These and these are mirror. These and these are mirror reflection. We are talking about anthracene molecule. Quantum yield of molecular fluorescence is simply ratio of number of molecules that fluoresce to total number of molecules that absorb light, or ratio of photons emitted to ratio of photons absorbed. Highly fluorescent molecules, such as fluorescene, have quantum efficiencies that approach 1. Species that do not fluoresce or show very weak fluorescence have quantum efficiencies that are practically 0. Most of non-ring compounds have 0 fluorescence. Compounds containing aromatic rings give most intense and most useful molecular fluorescence emission. Bigger rings or conjugated rings, better fluorescence is. So good fluorescing units are like these, or these, or these. It's important how rigid your molecule is. More rigidity, less vibrations, less chances that energy will dissipate into vibration or rotational units. So fluorine molecule has very high quantum yield. It's even named after fluorescence. And biphenyl molecule, the only difference, it's non-rigid, so there is some rotation possible here, or better say some flexibility of ring position. Quantum yield significantly drops down. Now let's look at some algebra. So incident light is coming into our cuvette, and emergent light is coming at other side. So we have Beer's law to describe this. Now, from Beer's law, we know that ln P1 minus ln P0 will be negative molar absorptivity, concentration in molarity units, and length of cuvette. Re-emitted light will be absorbed light in cuvette and some coefficient proportionality. It's not quantum yield because photons are flying at any direction from here, and we are collecting only a small fraction of them. So it's just coefficient of proportionality. Amount of absorbed light is P0 minus P1. So emerged, incident, the difference is absorbed. Now from this equation you can say that P1 is P0 and exponent minus epsilon CL. So we can put P1 in this equation and receive such an equation substitution. So P0 and P0 is present in both parts. You can take them out and receive such function. Again the same. P0 minus P1, and we have an equation for intensity of emitted radiation as function of concentration. No, this is not a straight line. It's exponents, it's complex and very unpleasant. But if absorbance is small, this value is absorbance. We can write that e power x can be simplified. What is e power x? Mathematicians say that it can be simplified as 1 plus x plus t something else. So if we'll put this again for small absorbances only, which means small concentrations only, we'll have x in here. So we have such a simplification. Instead of exponent, we have linear function. Now we can put this linear function in our equation above, and we have a linear equation. So intensity of emitted light, if absorbance is small, is proportional to k, intensity of incident light, and then molar absorptivity, concentration, and length of cuvette. As a result, we have such a scheme. We have incident light, absorbed light, emergent light with Beer's law, and re-emitted light, which intensity is proportional to molar absorptivity of your species at these wavelengths and concentration of our analyte, which is important to us. Now, this is true only at low concentration. We should expect straight line calibration for low concentration and some unpleasant curve for high concentrations. Now, sensitivity is proportional to power of source. So we want to use very strong lamps to have high sensitivity of our fluorescent method. And this is an example of calibration curve. As you can see, at very low concentrations, 10 to the negative 7, you have a straight line, and then it becomes a curve and becoming flat. So you can work in this area. Fluorescence methods are used to study chemical equilibrium, kinetics, action same way as absorption. Often it's possible to study chemical reactions at very low concentration because of much higher sensitivity of fluorescent method. In many cases, when fluorescent monitoring is not feasible, fluorescent probes can be bound covalently to specific sites of molecules such as proteins, making them detectable by fluorescence. Among compounds types that can be determined are amino acids, proteins, coenzymes, vitamins, nucleic acid, alkaloids, porphyrins, steroids, and so on. For example, when you need to analyze some type of nucleic acid that is responsible for this pesky virus, you want to attach fluorescent label to your reagent, so very small concentrations will be detectable. How this can be done? We have plenty of derivatization reactions that run with very high yields. For example, if you have amino group like that, you can run reaction with non-fluorescent tungsten chloride, and your resulting compound will be highly fluorescent. So we have reactions for amines, primary amines, carbonyl groups, SH groups, and many others. You can find full table in your textbook. As a summary, fluorescence is very powerful procedure allowing us to detect very small amounts of different chemical species.